project that I have with Jens Markov about a dynamical approach to the method by Bombieri-Iwaniec to bound exponential sums. So we're going to start with an exponential sum in d variables. So first, d is going to be 1 or 2. And it's going to be fairly general. We're going to put a pretty standard assumption on our phase f. So here we can think like a polynomial of degree at least 4. Or a pretty important example would be a logarithm, especially for one variable due to the connection to the Riemann zeta function. So kind of a very classical result going back to maybe the 1920s is van der Korpit. So if we assume that this f, telling us the size of the derivatives, is between m squared and m cubed, then we get this bound for our exponential sum. And this range for f is a critical range for subconvexity for the Riemann zeta function. This bound of van der Korpit quickly implies the while subconvexity. Zeta function grows like t to the 1/6 on the critical line. I mean, the chronology actually goes the other way, though. The first improvement over the van der Korpit method, at least in the subconvex range, came in the 1980s by this method of Bombieri and Iwaniec. So their method, I like to kind of think of happening in 2 stages. So the first stage is what I've heard, I think by Huxley, described as a discrete circle method. The second stage happens as a harmonic analysis. I think it's worth noting that every subsequent improvement on zeta subconvexity has come from improvements on the second stage. And so here we should think about, so for example, the current record comes from Bourgain's theory on decoupling. So this project started because Jens Markov and I were talking about this first stage, this discrete circle method, and we were wondering if we could find a dynamical approach to this discrete circle method. And kind of the two reasons for that, why we were interested in this. First of all, perhaps we could develop a method for bounding exponential sums in several variables, and also more speculatively, we could also imagine maybe bringing in equidistribution results from dynamics, and even in one variable, maybe we could dream of coming up with results there. Of course, life is not so easy, but still, the result that we get is it's still a little bit raw, but it's at least a little bit non-trivial, I would say. Here we go. We get this by, like I said, a dynamical interpretation of the first stage of the Bombieri-Iwaniec method. We do this in terms of what we call dynamics of theta functions that are defined via the Weil representation on the symplectic group. But kind of at a very important stage in our proof, we choose our parameters to simplify our analysis, and that's why we only obtain a bound that's of the van der Korpit strength. And of course, like I said, I think this project is still in its early stages, and I think we could. I'm still optimistic that we can push this further. Of course, I think this will require more sophisticated combinations of the harmonic analysis with dynamics. Okay, so So our theta functions are defined like this. We have a Schwartz function, and we sum it over the integers of the Weil representation. And kind of the important example to keep in mind is that if our symplectic matrix is in this parabolic, then we get this quadratic form in the phase. Okay, so that's important because the way that the Bombieri-Iwaniec method works is that if in our sum, so this first line here, we start with our exponential sum. We assume, well, at least in the case of summing over a square, we can approximate the indicator function of a square with a convolution. And this is very much like a van der Korpit shift. We approximate it by a convolution. We open up the convolution, change the order of summation and integration. But now, well, whereas van der Korpit does the Cauchy-Schwarz, Bombieri-Iwaniec do a Taylor expansion to second order, and that's where we see the theta function come in with the quadratic form. Now, one kind of key fact that is important for us in maybe the next slide or the slide after is the fact that into our Schwarz function here, phi that we feed into the Shale-Veil representation, we put in the remainder term from our Taylor expansion. And this is going to be why we have to very crudely choose our parameters. And that's going to be what causes our results not be so strong. Hopefully we'll get to that in a second. So now, okay, so now here's where we're gonna depart from Bombieri-Iwaniec. So Bombieri-Iwaniec, once they get this quadratic phase, they do a Diophantine approximation combined with some Poisson summation and computing some Gauss sums. These words, should all sound familiar to just automorphy of theta functions, right? And so maybe it shouldn't be surprised that we can bound our theta function in terms of basically just heights, gamma SB2 SB2Z invariant heights on the symplectic group. I think it's kind of funny. So in dynamics, they like to call these invariant heights Margulis functions. Why you attribute this to Margulis is maybe a simple idea, but if you see how Margulis uses these things, you might agree that we should attribute them. We should call them Margulis functions too. He's really quite skilled with them. But the key. I think the key takeaway here is that this uniformly Schwarz condition here, and that this family of functions phi that we apply, that we use in our theta functions, because of this extra phase coming from the remainder term of the Taylor expansion, we have to choose our epsilon. We can't choose our epsilon very big, and that's really what limits us in our analysis. And so going forward, we're going to have to prove some more complicated version of this, which we actually have more complicated versions of this. It's just more difficult to handle dynamically. Okay, so now we've arrived at a problem purely in dynamics, which is we've bounded our exponential sum by an average over a translated unipotent segment in G mod gamma, G the symplectic group, gamma the integer symplectic group. And we want to try to bound how much mass of this unipotent segment is escaping into the cusp. Now, what to me makes this problem pretty cool, and probably the last thing I'll be able to say before my 10 minutes is up, is that here, so as X here is a symmetric matrix, so this is like a three-dimensional horosphere, you would say, so the horosphere to this translation is three-dimensional, whereas here our second derivative matrices, the parameter here is two-dimensional, so we have a very small subset of our full horosphere. And so in terms of dynamical systems, this makes this problem actually fairly difficult to study by spectral methods or what I would consider more classical techniques. And so this is where more modern techniques of homogeneous dynamics tend to shine. And I'll stop here.